Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're looking at conservation of energy with dissipative forces, namely friction. Let us give you an example of conservation of energy without dissipative forces. Let's take a tennis ball, a slope, and let's roll the ball down. And the ball doesn't seem to lose any energy on the way, it just carries on its merry way. Now let's take another ball. Looks very smooth, but let's try the same thing. You see how it grinds to a halt. What we have here is a ball with sand in it. So when we roll it down the slope, it loses its mechanical energy. In other words, the potential energy at the top here gets converted into kinetic energy, but all the while it's being changed into friction. And one can in fact hear that some of the energy is being dissipated as sound, a very little bit, but most of it is turned into heat, even though we would not notice the difference. So let's apply a particular formula which we have to be familiar with. Work done by non-conservative forces, namely friction, is equal to the change of kinetic energy plus the change of potential energy. Now whenever we see change or delta, we should immediately think that a change of anything is always the final, EK final, minus EK initial. So that is what change of kinetic energy is equal to. The final state minus the initial state. Plus, what would a change of potential energy be? It would be EP final minus EP initial. See how we've used subscripts to identify all of our factors. So let's apply that equation to this situation and let's find out what was the work done by the non-conservative force of friction as this rolled down a slope and came to a halt. How much work in fact was lost? So let's start with what was its initial kinetic energy? Well, if it's going at 0 kilometers or meters per second, and we know that EK, let's see, we can write it here. EK is equal to a half mv squared. Half mass times velocity squared. But if we have a velocity of 0, EK becomes 0. So if it's not moving, it's got 0 kinetic energy. And when it ends, it's not moving, so it's got 0. So what is the final kinetic energy? Naught. Minus what's the initial kinetic energy, naught, plus what is the final potential energy. Now how do we work out potential energy? Well, as something rises, it gains potential energy. And as it drops, let's call this its ground state. It's got 0 potential energy anywhere along here, but as it is lifted and placed on there, it gains potential energy. So its final state is 0 potential energy because it's at its lowest point. So EP final is going to be equal to 0 because it's sitting there, minus EP initial. Now what is potential energy defined as? Well, we have a formula, it's in our data sheet. EP equals mgh. mgh. So let's find the mass of this ball by weighing it, and we know what g is and we know what h is. So let's get a spring balance and let us weigh it. So here is our spring balance. Here is a bag, and let's weigh this ball. So our spring balance has been zeroed, we drop it in there, and we read it, and it comes to 70 grams. 70 grams is the mass of our ball. But we don't work in grams, we work in kilograms, so we're going to divide that 70 by 1,000. So let's apply our formula. Mass is 70 grams converted to kilograms divided by 1,000 is 0.07 kilograms. That's the mass. Times G, which is 9,8, times height in meters. Let's measure the height that our ball was raised to using this, and it is 0.135 meters. 0.135 meters. 0.135 meters. So, multiplying that all together, we've got 0.07 times 9.8 times 135 equals, and we get 0.0926. So this all adds up to 0 plus 0 minus our answer, so it becomes not plus but minus 0.0926, and our answer is measured in joules. So notice our negative answer. What does that mean? It refers to the fact that if this is our direction of displacement, the work is done, friction is done in the opposite direction, and when that occurs, we get a negative quantity for the amount of work done. In conclusion then, we see that our total work done by non-conservative forces is equal to minus 0.9, and it's in joules. All that the zero denotes is that the work done is opposite to the direction of motion by the ball. So the negative denotes that the work is done in the opposite direction to what the ball is moving. Now we're talking about non-conservative forces and the work done. How about, just for fun of it, we work out the frictional force of this ball. The way we're going to do it is as follows. We're going to allow our ball to roll from the top and come to a stop. And we're going to use the formula work done equals force of friction times delta x, or displacement. Now we know that our work done is minus 0.09 joules. So this force times displacement is going to be equal to minus 0.09. And that is equal to the force times the displacement equals force of friction times displacement. Let's measure the displacement of the ball. So we dropped it from the top there and it rolled 0.47 meters to here, from here, the top, to here at the bottom. So it's 0.47 meters times 0.47 meters, and therefore force of friction is going to be equal to that divided by that. In fact, what we're going to do is divide both sides by 0.47 That cancels out, and there we see our frictional force is equal to 0.09 divided by 0.47. So 0.09 divided by 0.47 equals 0.191. So that is going to be equal to 0.19, and notice the negative, and the answer is in newtons. So it is equal to minus, there's our negative, minus 0.19 newtons. So what does the negative force mean? The direction of motion is like this. Frictional force was opposed to motion. So when we talk about our answer, we explain this negative, we explain it by saying opposite to motion. That is the direction, opposite to motion, and there we have it.